As an aerospace engineer, I get to have a lot of fun working with rockets. But you never just launch a rocket and see where it goes. A rocket always has a destination, and understanding projectile motion is crucial for being able to correctly navigate a rocket to its desired destination. A rocket is equipped with special sensors that engineers use to get information about the rocket's position and velocity. Rockets go really fast, and because they travel at such high speeds, it's really important during the entire flight time to always know the exact position and instantaneous velocity. Otherwise, if the rocket strays off course and we don't correct its trajectory, we won't be able to successfully navigate to the place we're trying to go. Projectile motion is used in many large engineering projects, such as rocketry. But the principles of projectile motion can be tested through a simple ball launcher experiment. First, the ball launcher is placed next to a long table. The angle that the table makes with respect to the launcher is called theta. The positive x direction is parallel to the table and points to the right of the launcher. The positive y direction is perpendicular to the table and points above the launcher. By placing the launcher at an angle to the table, firing the ball creates a velocity in the x direction, Vx, and a velocity in the y direction, Vy. The combination of these velocities, Vx plus Vy, creates a parabolic motion when the ball is launched. The path the ball follows can be characterized by theta and the initial velocity imparted to the ball by the launcher. The initial velocity of the ball was measured using a calculator and an infrared sensor. The infrared sensor on the C fixture shines a light beam across its two arms. As the ball passes between the arms, it disrupts the light beam. The sensor knows when the ball passes by because it can detect when the light beam is disturbed. A calculator, which is hooked up to the sensor, measures the length of time between when the ball leaves the launcher and when it passes the sensor. By knowing the distance between the launcher and the sensor, and the time it took for the ball to travel that distance, we can calculate the initial velocity of the ball. The experiment was performed multiple times at various thetas. For each trial, the initial velocity, theta, and the distance traveled in the x direction were all recorded. Now it's your turn to finish the experiment. You will receive a data sheet showing all the measurements recorded in the ball launcher experiment. Plug in the values of the thetas and initial velocities from the experiment to the projectile motion equations you have learned in class, and then calculate how far the ball should have traveled. Then compare your calculations to the measurement from the experiment to see if they match. If there are differences between your calculations and the experimental measurements, think about what might be causing those differences. If you want an additional challenge, try solving for the maximum vertical height and the time of flight.